But yes, so be ready for the test next week. Look at the study guide. See if you have questions before we do the in-class review. But yeah, so this week we have so 2 more days. We don't have school on Friday. And we're going to get through chapter 7. At the end of chapter 6, we introduced this concept of the ion. Who can tell me, what is an ion? Anyone? What is an ion?
It's part of the molecule, right?
It's an atom.
It's positive, right?
Has a positive or negative charge. Great. Why? Why does it have a positive or negative charge?
Because it's science.
Okay, let's get a little more descriptive than that.
Okay. Hold on.
Okay, we have a different number of electrons and protons. Okay, remember, electrons are negative, protons are positive. If we have the same number, it's electrically neutral. Okay? But if we don't have the same number, it's got a charge, and that becomes an ion. Okay? Now, we need to get a couple more vocabulary terms. Okay. Now, just so that you understand, this is pronounced cation. Okay, it's not cation. It is cation. This is an ion. It's not anion. It's an ion. Okay. So cations are positive. Anions would then be negative. So how do you remember that? Cation is positive. You laugh, but you are going to remember that. It is. It's super dumb, but you're going to remember it, aren't you? So, a cat has pause. Cation is positive. Super dumb, but it works.
Who cares?
Yep. So, so how do we get a cation? What has happened? What has happened to make this atom?
You electrify it.
There's more protons. Now, it's not impossible to add a proton to an atom, but it's pretty difficult. It's much more likely that instead we have lost an electron, and that's why we have more protons than electrons. Remember, we talked about ionization energy, the amount of energy it takes to remove an electron. Okay. The other thing that we want to mention, and we did talk about this, how can we tell whether something is more likely to become a cation or anion? You remember? How can we tell whether something is more likely to gain or lose an electron?
Oh, with electronegativity.
Okay, that plays into it, for sure.
The negativity chart.
There's an easier way to do it, but that does play into it.
Periods.
So close.
Periodic trends.
Not periods, but groups. There we go. Groups.
That's what I meant, not trends.
So if we look at our periodic table up here on the wall,
First line, top line.
number 1. What do we think? Is it more likely to gain or lose an electron? More likely to lose. Why?
Because it decreases.
Okay. Because if it loses that one valence electron, we go down to the next layer of electrons, the next quantum layer, and it is a full valence shell because it has the electron configuration of a noble gas if group 1 loses one electron. Okay. Remember, group 1, 2, and 13 are more likely to lose electrons. And the numbers that they lose are 1, 2, and 3. Okay. On the other side of the periodic table, groups 15, 16, and 17 are more likely to gain electrons because it's easier to grab a couple of electrons than to lose 5, 6, or 7 to go down to the next layer. Easier to fill it up for the rest. So, okay. Now, that, if you were paying attention, you noticed we skipped over groups 3 through 12. Okay. Those are metals, transition metals, and things like that. Those are going to be, well, it's hard to say exactly how many electrons they're going to lose. The transition metals, well, I'll just say they're a little bit more, you have to memorize, okay? Now, I'm not going to expect you to memorize all the transition metals and their ions that they form, okay? We are going to focus on the ones that we just talked about, groups 1, 2, 13, 15 through 17, okay? 14, like I said, it's more likely that they're going to lose the electrons than gain them, but they become very reactive and we don't see them very often. So instead, with the transition metals, well, the real problem is that transition metals can do multiple things. So sodium in group 1, it's going to lose one electron. Done. It loses one electron, and that's the only thing that happens, really. Can other things happen? Yes, but they're unlikely. Iron, however, is pretty much just as likely to lose 2 as it is to lose 3. Okay? And that's true of a lot of the transition metals. Okay? For the transition metals, if you guess 2 or 3, you're probably going to be pretty safe. But not all of them follow that pattern, and so it's safer to look it up. Anyway. They will, however, still lose electrons. Metals actually, by their nature, are very willing to give up electrons. There's really not a strong interaction between the electrons and the protons in metals. It's just kind of the way they are. Because we have some of these groups, these transition metals that may or may not lose a certain number of electrons, they will not always follow the octet rule. Okay? Instead, what they can do is have what's called a pseudo noble gas configuration. I just want to point that out. It is in the book. I'm never going to ask about it again. I just want to point that out in case you see that in the book. So, okay. So that is how we form these ions, basically. Okay. And now, for the first time, we are going to talk about bonding. We're going to take 2 atoms, and we are going to stick them together. Now, there's a lot of different ways that this can happen. The first way that we are going to talk about deals with ions. In fact, we call it ionic bonding. Ionic bonds are, well, they're not true bonds. They're more of interactions. Just like if I have these 2 magnets here, okay? Yeah, they're stuck together. These are pretty strong magnets, so they're stuck really well. But sometimes I have to put this back on something to pull them apart because they're actually really strong.
What are they?
These are neodymium. Well, there we go. But you can take them apart, okay? But then when you bring them close together again, way, they'll come right back together. That's more of what we have with ionic bonds. They're not permanent. They're a little bit more flexible. Okay? But the way that ionic bonds work is really you have cations that are positive and anions, which are negative. And remember, positive and negative, they attract each other. Ionic bonds are all about charges. We have opposite charges that keep these atoms together. Opposite charges that keep these atoms together. It is, well, because of that, we have some very specific properties which we'll get into. Okay? But when we have ionic bonds, that creates what we call an ionic compound. Now remember when we talked about some definitions a while back, a compound is when we have two or more elements stuck together. Now, they can be in a permanent covalent bond. We'll get to that after the test. But it also can be in this ionic bond. Okay. A lot of our ionic compounds are what we call binary. Anyone want to guess what that means?
I know.
What does BI mean?
Bio.
Not bio. It's not on the periodic table. It means two. Two. BI means two. So binary, so if you're familiar with computers and binary code, the reason why it's called binary is because it can either be a 0 or a 1, and that's it. There's two options. Okay. Binary ionic compounds, kind of the same thing. We have two things. Okay. And in the book on page 210, there is an example of a couple of these binary ionic compounds. Okay. Picture A, where they have that flask and it's sort of green, that is the reaction between sodium and chlorine. Now, this is a compound reaction that we are going to discuss over and over and over. Okay. So we have sodium metal plus chlorine gas. And it gives us sodium chloride. We do have to put those there for balancing. We haven't talked about balancing yet. We'll get to that. So, sodium plus chlorine gives us what's called sodium chloride. What is sodium chloride? Anybody know?
A mixture of sodium and chlorine.
Okay, but what is it? Salt. If you put salt on your food at lunch, that's what you put on your food. Sodium chloride. Okay? You can generate that in a lab by taking sodium metal and chlorine gas. So what's actually happening? So remember, chlorine has 7 valence electrons. It wants 8. Well, sodium, remember, it has that extra one that it doesn't really want. And it does take a little bit of energy to get that electron off. If you remember, when we looked at page 192, the ionization energies, even for that group 1 element, lithium, to get rid of that first electron to get the full valence shell, it still needed energy. But, and this is getting ahead of ourselves just a little bit, so that if this doesn't make complete sense, don't stress. The resulting compound has less energy. Okay, there's energy that is released, which allows this to happen. Okay. Chlorine wants that electron bad enough to actually physically take it from sodium. That electron will no longer be associated with sodium. It will associate itself with chlorine, which means we have Na plus and Cl minus. And because they have these opposite charges, they attract each other. Okay. The other example is magnesium oxide, which is the result of burning magnesium metal. You guys seen that? Magnesium metal burning? Maybe we'll have to go into the lab and do that sometime, because it's kind of cool to see. As you can tell from the picture, it is very, very bright. That picture doesn't really demonstrate just how bright it is. But yeah, it's super, super bright.
It's like almost dark.
Anyway, when we get these compounds, like we said, the electron physically moves from what is going to form the cation, and it leaves that orbitals. It leaves the entire set of orbitals and becomes part of the anion. And that is how they stick together. Now, the other reason why ionic compounds, ionic bonds, are not truly bonds is because they don't form true molecules. Now, if this was a true molecule, we have this, and that would be it. It would just be its thing, okay? But what happens is, well, guess what? We have a negative right here. And just because there's a positive on this side doesn't mean we can't put another one right here. And now we have a positive there, which means we can put a negative. And we don't just have to build a line. We can do this. Okay. We can continue building like that, and we can build in the third dimension. Okay. So this is on 213. Yes. That is a magnification of a piece of salt. Notice it does have the straight, flat edges. The reason for that is it builds this crystal structure. If you ever need to tell the difference between sugar and salt without tasting them, you can look really close. Salt is going to be squared off. Sugar will not be.
Sugar's just like more powdery, right?
It's not a regular square shape. I mean, it can have pretty much the same texture, but it won't be in perfect squares like salt is.
I can imagine something horrible putting sugar in my thing and salt.
Yeah, or if you're baking cookies and put in a cup of salt instead of a cup of sugar, that's gonna taste horrible.
Yeah, I know one time my brother was making cookies and he's like, oh, I'm supposed to do that usually this down and then the salt. I'm like,
Yeah.
He's like, why did it taste better? Like I told you. Yeah.
So now this is what we call a crystal, a repeating pattern. Crystal chemistry gets very complicated very quickly. We're not going to do very much with crystal chemistry at all. Just understand we get this repeating pattern, and it can be different shapes. It can be different shapes based off of what we have in there. If you look at page 214, you can see some ionic compounds and the shapes of the crystals that they create. But really, it all comes down to the interaction between the positive and the negative. Okay? The things on the right side of the periodic table, they want that extra electron. They want to become negative so that they can get their full valence shell. The things on the left side of the periodic table, they are willing to give up that electron in the right circumstance to get down to the full valence shell. And when that happens, we get opposite charges, and that causes them to attract to each other. Okay? Now, we're going to talk about some generic properties of these ionic compounds. These are not going to be absolutely true for every single one. These are general properties. So just understand that you quite possibly will run into some ionic compounds that don't follow this set of rules. But anyway, we are going to go through a couple of them. The first one that we want to talk about is melting and boiling points. Melting and boiling points. These are typically, the interactions are typically pretty stable. The interactions between these positive and negative are strong enough that they don't really want to melt. Because when things are melting, that means all of these are now fluid and rolling across each other, and they're not staying in that crystal anymore. So most ionic compounds have fairly high melting points. If you look, sodium chloride, you can take salt and get it to melt. Okay?
I want to see that.
Now you do have to get it over 800 degrees Celsius.
That's what.
So you probably don't necessarily have the equipment to do that. So don't go home and try and melt salt. Okay? Because, yeah, it's not something that you should try in your kitchen.
What's the degrees in Fahrenheit?
For those of you who grew up with Fahrenheit, let me do the conversion.
This is like some weird number.
So 800 degrees Celsius is 1,472 degrees Fahrenheit.
18,000 is easier than what I wrote there. 14,874.
1,472 degrees Fahrenheit. So I'm guessing none of your ovens go that hot, so don't even try.
What about a blowtorch?
It would have to depend. Some torches can get that hot, but not all of them. Okay. We also can continue to heat salt and can eventually get it to boil. That requires a whole lot of heat.
Bunsen burner.
Bunsen burner. Maybe if you have it adjusted correctly. Also, it probably depends on what sort of fuel you're using for your Bunsen burner. So, what's the best way to melt things?
Yeah, like more like what chemicals go to melt things?
Chemicals?
Like butane, propane.
Oh, honestly, it's less a matter of chemicals and more a matter of equipment. Because if you can get, like if you have a kiln, what that does is a lot of the heat builds up inside of it and it holds that heat. Whereas if you just use the same fuel, but it's not inside the kiln, the heat dissipates really quickly. So you want to be able to build up heat if you want to get really high temperatures, rather than just have something that burns really hot. Anyway, now there's an interesting thing that happens when we heat ionic compounds to where they can melt. And since these ions are free to move now, we can use melted salt to conduct electricity because the ions can move. Okay? When they are in a solid crystal lattice, most ionic compounds do not conduct electricity. But if you get them to melt and they can move around, they do. Can you think of another way that you could get these individual ions in salt to be able to move around?
No, never mind. I was going to say freeze, but still.
No, this makes it solid. What? Dissolve them. Very good. We dissolve them. You put salt in water, it dissolves. It's going to dissolve. And those ions are going to break apart, and they're going to allow you to conduct electricity through water.
Isn't that how you make an egg float?
That's one way to do it. By adding enough salt, you can get buoyancy. The truth is, water by itself is a very, very poor conductor of electricity. But if you put some salt or really any ionic compound, it all of a sudden is able to conduct electricity because it has these ions in it. When the ions are dissolved, we call them electrolytes. Now, maybe you've heard that word electrolyte when, like in a commercial for like Gatorade. Gatorade has electrolytes in it, which is a fancy way of saying Gatorade has salt in it. Now, it's not just sodium chloride. There are other ones like potassium and things like that that your body needs and loses when you sweat. But electrolytes sounds a lot better than trying to advertise Gatorade by saying, here, have some sugary salt water. But that's what Gatorade is. Well, that's what marketing is.
Exactly.
So, anyway, a couple of other properties that it talks about. They're usually pretty strong because of the interaction here. There's a lot of interaction between these positive and negative. But they are brittle. If you crush them, hit them with a hammer or something, they have a tendency to fracture along these crystal planes. So, anyway. Decided we're not going to talk about energy. We're just going to ignore that for now. So that's actually all I wanted to get through today. We do have some extra time, so before I let you get started on your homework, why don't we just go to the lab and I'll burn some magnesium for you. Sounds like fun.
Explode that.